Chapter 2, M100ST Robot Design including Base Camp Spec. Mission: Tunnel Building, Arcadia Plains, Mars. Base Camp: Energy, Solar Farm, Battery Array, Fission Power Plant, and Thermal Management. Base Camp: Resource Processing, Magnetic Separators, Flotation Tanks and Centrifuges, Carbothermal Reduction, Hydrogen Reduction, Air Compressor and Cryogenic Separator, HCl Electrolysis Production Cell, Controlled Atmosphere Reactor, Nitrogen or Argon from Cryosep. Distillation Columns. Base Camp: Manufacturing Equipment, Basic. Basic Machine Shop, Drills, Lathes, Saws, Laser Cutter, Engraver, Cleaners. Base Camp: Manufacturing Equipment, Advanced. Redwire Class 3D Printer, 0.1 millimeter resolution by 50 cc's volume, plasma coating, electrodeposition, flame spraying, quote unquote, etc. Electrospinning rig with rotating collector. 1600C capable ceramic furnace. Precision grinders with diamond and silicon carbide wheels. Mixing, tumbling, and polishing chambers. Compression molds and jigs. Pultruder tooling for fiber and silicone resin. Ball mills with ceramic grinding media. Water purification and recycling system. Atmosphere management system. Laser metrology system. Materials handling. 2 Tesla bots. Construction equipment. Cybertruck style platform with attachments to convert or transform into various types of construction equipment such as bulldozer, excavator, skip loader, etc. Design and specifications. M100ST robot. Mass 407 kilograms. Body length 1.5 meters. Body outside diameter maximum 36 centimeters. Body outside diameter minimum 10 centimeters. Body inside diameter maximum 15 centimeters. Body inside diameter minimum 8 centimeters. Power: 1000 psi compressed CO2 in 24 fiber-reinforced tanks. Drivetrain: pneumatic gear motor actuation, basalt fiber-reinforced silicone synchromesh cable drive. Propulsion: 6 bidirectional synchromesh actuator arms. All systems joints protected and sealed with silicone foam. Control system: pneumatic and mechanical logic. No semiconductor manufacturing is available on Mars. Description: the first requirement of survival is not food or water, but shelter. The harsh surface of Mars features near vacuum CO2 atmosphere, up to 78 km per hour abrasive sandblasting, and 233 millisievert radiation frying. However, the Arcadia Plains feature wide areas covered with loose regolith, perfect for building. The M100ST has several variants. Let's start with the M100STF, the foam liner. First, the 155 Mars kilogram robot is towed into place with a suitable vehicle, such as a Cybertruck, and placed on the ground. The M100STF then uses its mass in conjunction with worm-like twisting motion, 40 Hz vibrating ceramic scales, and a bit of compressed CO2 to liquefy the regolith and burrow in. Once completely buried, the M100STF moves forward about 30 to 50 centimeters while opening and closing its jaws, which have been modified with a baleen-like fiber-reinforced silicone screen. This only allows 5 millimeter or smaller regolith particles to enter and travel towards the tail. Executing a twisting motion, the screened regolith is moved and tumbled toward the tail. 3 tanks used compressed CO2 to spray materials on top of the mix while it is being tumbled. The tanks have normally closed gravity-operated valves, only opening when within 30 degrees of 12 o'clock. Tank A sprays an aqueous solution of 8 to 12% perchlorates with 4 to 6% silicone polymerizer foaming agent. Tank B sprays a mixture of 3% iron and pozzolana powder. Tank C sprays reinforcing flake filler. The resulting mix is extruded out the tail orifice in a circular motion, foaming and expanding in the near vacuum of Mars, sealing off a cylindrical section about 30 centimeters in diameter and 50 centimeters long. The cement foam then self-pressurizes and seals off for cure. The tail continues moving in a circular motion, working the foam against the walls for about 1 minute, then relaxes to center position. After full cure, the M100STF moves forward another 50 centimeters and repeats the process. Teams of M100STFs can thus preform large sections under the regolith. After full cure, these ready-made cement foam sections are then cut open, cleared, and built up to final desired condition. This brings us to the next variant, the M100STM. In this mode, the jaws do not have the silicone baleen, and tanks A, B, and C are loaded with different ingredients. Tank A now has 15 to 20% perchlorate solution. Tank B, 60% volcanic glass, 30% iron powder, 10% crushed plagioclase. Tank C, short chopped basalt fiber. Thus, the M100STM functions as a portable fiber-reinforced concrete mixer extruder. Just add regolith. Martian concrete outperforms Roman concrete, and indeed, Arcadia cement and self-sealing cement foam, along with methalox fuel, are exported from Mars and used all over the system. The third variant is the stripped-down M100STE, which basically is used as an excavator or conveyor belt, using pressurized CO2 and 40 Hz vibration to liquefy and propel scooped regolith or other loose materials through itself and out the tail. The M100STE is equipped with a 5 centimeter fiber-reinforced silicone baleen. Rows of MST100STEs can be daisy-chained to cover long distances, acting like conveyor belts. In conclusion, the M100ST series robots, aka the sandworms of Mars, are a critical component not only of Martian infrastructure, but Martian exports as well. Martian rotovators put shipments out for delivery. Arcadia cement and self-sealing cement foam are valued for their ability to self-seal, self-pressurize, cure, and vacuum with little or no gravity, high strength, radiation resistance, and corrosion resistance, helping to build orbital habitats and other structures throughout the system.